Okay, this will be a short video just kind of trying to discuss when and where you might use this adjugate formula for the inverse, this formula for the inverse of a matrix in terms of determinants, right? We know that the adjugate matrix is a matrix of cofactors. Each cofactor is a determinant. We mentioned in the last video that, for 4 by 4 and higher, you've got to calculate a lot of determinants to use this formula. It's really a lot of work, right? For 2 by 2 and 3 by 3, it might be marginally faster than doing row operations, but once you hit 4 by 4 and higher, the previous algorithm using row operations for finding the inverse is much faster than this adjugate formula. So where would you use the adjugate formula? Well, you might use it if you were dealing with matrices that, let's say, have well, maybe you're doing this by hand and you've got decimals or irrational numbers or something like that, where you're not going to be able to do row operations in your head, right? You can't, or even on paper, right? Row operations with decimals, that's going to be annoying, right? But you could calculate all your cofactors. You can calculate those determinants. You can punch them into a calculator, get those numbers out. And come up with your entries. So that's maybe one place where you might use it. The other place where you might use it is if you're dealing with matrices that have functions in them. you know, if I had, these are things that might show up in Calculus 4 and differential equations. There are a number of places where you might encounter matrices with function entries. And so if I had, if I had something like, let's say I had something with polynomial entries in it, x squared, you know, x squared minus 4, x minus 1, something like this, right? Well, one of the things that's nice about this is that I can calculate. Notice that the determinant is kind of, it's given by multiplying entries, and so if I have a matrix with polynomial entries, the determinant is also going to be a polynomial. 2x plus 1 times x minus 1 minus x squared times x squared minus 4, right? I get 2x squared plus minus x minus 2x plus 1x minus x minus 1 minus x to the fourth plus 4x squared, right? So I get I get this minus x to the fourth plus 6x squared minus x minus 1. Okay, right? And so I could also, if I wanted to, I could calculate the adjugate. Right. So what's the adjugate going to be? Well, the 1, 1 cofactor, if I delete row 1, column 1, I'm left with x minus 1. The 1, 2 cofactor, I delete row 1, column 2. That gives me x squared minus 4, but it comes with a minus sign because 1 plus 2 is negative, right? But that cofactor, because I'm doing the transpose, it goes down here. So I get minus x squared minus 4. And then here, similarly, I'm going to get minus x squared, and then finally I get 2x plus 1 there. And so if I wanted to get the inverse, right, the inverse would be, well, I take each of the entries in this matrix, I divide by this polynomial here, and I would have a formula for the inverse in terms of rational functions. And then I could, work out maybe values of x for which this polynomial happens to be 0, if there are any, and decide, for which values of x is the inverse defined. Okay. Here's another example. This is one you might see in Calc 4, or maybe in a physics class. You've got a problem in 3 dimensions where you want to transform into what are called the spherical coordinates. Well, I don't know if I want to get into the details here, but you've got a sphere. So the idea is you've got a point, so you locate that point on a sphere of radius rho, and this, and you've got 2 angles here. You've got an angle of theta down there, and you've got an angle phi up there. Not important. I'm not going to ask you about spherical coordinates, but this is a change of variables that you can do, which can be very useful in a lot of integration problems. And one of the things that you need when you're doing these integration problems is you need the determinant of a matrix of partial derivatives, which looks something like this, right? And you want to know, okay, for what values of these spherical coordinates, rho, theta, and phi, where is this thing going to be invertible? That turns out to be important. Well, one of the ways you can figure out where it's invertible is by computing the determinant. The other reason why you want this determinant is, so this is called the Jacobian. This is called the Jacobian of t. It's a function of rho, theta, and phi. It's the determinant of this matrix. Turns out this comes out to be rho squared times sine phi. Okay, it's a fair amount of work to get there, but you can show that's what you get. Remember that determinants also have something to do with volumes. This quantity gives you sort of a distortion factor. It's telling you how much volumes are changed when you do this change of variables, and that's something that's important if you're doing, let's say, a triple integral where you're computing volume. So that's one example where you might, let's say you want to figure out, well, where is it invertible? Well, it's going to be invertible where the derivative is non-zero, so away from rho equals 0 and the points where sine phi equals 0, so at phi equals 0 or phi equal to pi. And then also, of course, if you wanted to actually figure out what that inverse is, if you wanted a formula for the inverse, right, you're not doing row operations on this guy. You would much rather compute cofactors because that's much easier algebra when things are complicated like this. All right, so that is it for the adjugate formula.